Hey team, Andre from High Performance Academy here. Welcome along to our first members webinar for 2021. Been off over the summer for a little bit of a break like most of you, I guess, over the Christmas holidays. So hopefully not too rusty today. Hopefully I still remember how to do this. Hopefully everyone did have a good break. Today we are going to be covering idle speed control tuning on the ECU Master EMU Black ECU, obviously fitted to our Vision 11 Subaru STI. It's one of those things that I think is often overlooked or not correctly dealt with, and idle speed control, much like one of my other hot topics, which is cold start performance. In my opinion, it's really one of those things that makes a big difference, particularly for a street-driven car. We'd like, where possible, our idle speed control to replicate the sort of performance we'll get in a factory showroom stock car. So we'll get into that and go through some of the ins and outs of idle speed controlling on the ECU Master EMU platform shortly. Before we get into that though, there's obviously been a little bit going on over the last few weeks, and I just wanted to bring you up to speed. First of all, we have partnered with AEM in the US. They've given us one of their AEM CD7 dashes here, which I've got on display, and they are giving this away. We're adding to this with our suite of tuning courses, so a price package there somewhere in the region of about $3,000 US. So you can head over to the link that Scott is dropping into the comments to get your name into the draw. There are also a few other tasks that you can complete to give yourself a few other entries. So the CD7 has been around for a little while now. Obviously there's a lot of dash loggers and dash displays out there on the market. This is the logging version. Some of the nice functionality with this particular dash is that it does have the two tactile buttons on the side of the full color screen. Now, a lot of dashes don't have any ability to control any of their functionality from the screen. I personally think this is quite a nice touch. We've got the obligatory shift light module up the top, the ability to display your data in a range of different formats, the full color display as well, very easy to view just about in any sunlight conditions. Now, you can get data into that CD7 dash via CAN, which is timely because I'm going to be talking a little bit more about CAN as we go through this pre-show. So it's not just limited to AEM product. In fact, they've got a fairly wide list of supported factory and aftermarket ECUs. So as long as you're running something that is supported, it's really as simple as connecting up the 2-wire CAN bus, selecting the correct template, and you're good to go. So that particular giveaway, I'll just actually check there. We've got 2 weeks left for that to run, 14 days. So jump over to the link that Scott has put in the comments, get your name into the draw, make sure that you don't miss out. And also important to mention, doesn't matter whereabouts you are in the world, we will ship that to your door, so don't think you're going to miss out. Now, I just wanted to talk a little bit about some upcoming course content. Last year at HPA, we focused on adding a lot of worked examples to our existing tuning courses, and I know that those were valuable. They're going to help out a lot of people, and they were a lot of worked examples that we had been asked frequently about. For those who aren't familiar with what a worked example is, with our practical tuning courses, that's our practical standalone as well as our practical reflash tuning course, we teach a step-by-step process that you can apply irrespective of the platform or engine that you are tuning on. However, of course, every ECU and every OE factory ECU has its own intricacies in how we deal with certain aspects. So the worked examples are an informal walkthrough of the HPA tuning process, and you can watch them being applied from start to finish on real tuning jobs. So one of the last ones we added, for example, was on this Vision 11 STI using the open source ECU Flash and ROM Raider software to reflash the factory ECU. If you are interested, you can find those courses at hpaacademy.com/courses, but we're here to talk about what we've got planned, at least for the first quarter of this year. Right at the end of last year, I started work on our cam control tuning course. Now, I've got a few members webinars already there in the archive on this, but they are quite specific around a certain topic, and it's a little difficult to do justice to the entire topic inside of a 40 or 50 minute members webinar. So we decided to to get a little bit more involved and create a complete course. Again, this is something we've been asked for quite a lot. So for those who aren't aware, what is cam control? So often also referred to as continuously variable cam control. It's a method where the ECU can advance or retard the cam, or often both of the cams, while the engine's running, and this gives us vast control over the power and torque output of the engine. So just to have a quick look at what that actually looks like inside of an ECU, let's just jump across to my laptop screen for a moment. And this is the Motec M150 tuning software that we've got running. Motec M150 is running on the Toyota 86 turbo car that we've got here. And well, the specifics of the tuning software don't really matter, but this is the cam control target map for our inlet cam. So we've got numerically there, and of course we've got a little graphical representation of what that looks like out here. So a general principle with, at least when we're talking about our intake cam here, we tend to find that if we advance the cam, so it's opening and closing the valves earlier in the engine cycle, this is going to generally favor low RPM power and torque. As we retard the cam and it happens, the valve timing events happen later in the engine cycle, this tends to favor high RPM performance. So if we look, the load axis here is a little bit nonsensical. It's called engine load normalized. I'm running a pressure ratio on this particular engine, but generally, just if we take for granted that we're up around this area here when we are at wide open throttle, we'll actually just full screen that so we can see it a little bit easier. We can see at sort of 3 to 3,500 RPM where we are around about peak torque. We've advanced the cam in this case 30 to 35 degrees, but as our RPM increases and we move to the right of this graph, particularly once we get out to our rev limiter, I should say, out around 7,500 RPM, you can see we've retarded that back down to 2 degrees there, basically back to zero. So that's our general trend there. Now, back when I first started tuning, cam control engines were only just coming out. In fact, for probably the first 3 to 5 years of my career, cam control engines really weren't common at all. We didn't really see them. For this reason, a lot of the aftermarket ECUs that I dealt with had no facility to control variable cam control. Makes sense. Didn't exist. Why would they have it? What we then saw is, as they started to become a little bit more mainstream in terms of OE engines that offered cam control, we started seeing these filter into engines that we were retuning in the aftermarket. Some of the ECU manufacturers were a little bit slow and maybe a little bit hesitant to add in cam control functionality. And a common theme that I heard, and I do still hear this to a degree, is that it really doesn't do anything for power. Now, there is some truth in this, but it's not just power, it's our torque curve that we really need to consider, and the usability of the engine. So just to give you a bit of a look at what this can look like, let's just jump across to my dyno screen for a moment here. And this is some data that I captured while I was doing some testing for this cam control course. So the yellow and green graphs here, we can see there is actually a power difference up the top. It's not insignificant, 381 versus 352 horsepower. So this is with our Toyota 86 turbocharged engine, one run with our fixed cam control and one run with our optimized cam control. Green, obviously, fixed cam control. Look in particular here at the sort of difference we've got down at around about 4,000, 3,500 RPM. We're sort of seeing around about 70, 75 horsepower difference at that particular point. So for those who are arguing that cam control isn't something that's useful, then I don't have that same opinion. I tend to look at the results and it's pretty compelling. It's pretty hard to see a reason why we'd want to give away potentially that sort of power gain. However, the challenge here, of course, is actually setting this up properly, and this is 2 stages to the setup. First of all, we need to actually configure the ECU so it's getting the right signals, that it's controlling the right outputs. We need to make sure it's able to control the cams properly and track our targets accurately. Then, of course, we actually need to choose those targets. So that cam control course, we are still fairly early in the development. I'm still in the writing stages, but we're hoping to have that out first quarter of 2021. So that's something to look forward to. Now, while I've talked there about variable cam control, I'm actually making this course all-encompassing. So it will also deal with switched cam control systems, obviously much simpler, such as Honda's VTEC, Nissan VVL, etc. And we'll also be delving into the process of optimizing fixed cam control, so fixed cam timing with adjustable vernier cam gears, which we still see quite frequently as well. So that course, as I say, a little way off, but I know that's going to be really helpful for a lot of people. The next one we've got coming up, which we're just about to get into the filming of later this week. For those of you who are long-term HPA followers or members, you'll hopefully remember Zach, who was our wiring tutor. Zach unfortunately got poached off us by a local university a couple of years ago. However, we've still stayed in touch with Zach, and Zach's got a little bit more free time, so we've actually poached him back just for a little bit, and he is developing our CAN course. This is something, again, we've been asked for so often by so many people. So CAN, or controller area network, is a communication protocol that's really common in both factory and now aftermarket ECUs, and it's a way of sending data around a car between various modules. Particularly as far as the OEs are concerned, this has become more and more important as they've added more and more different electronic control modules. So we may have an engine control module, ABS module, maybe a module controlling the dash cluster, traction control, even air conditioning, and all of these modules require often some of the same signals. So rather than multiple wires running to all these modules, CAN is a simple 2-wire bus that sends all of the information out there, and the different modules can receive the information that they require. Now, this has become really prominent as well in the aftermarket world. We're seeing a lot of aftermarket components from different ECU manufacturers and non-ECU manufacturers for that matter that are providing products that deliver information via CAN. The nice aspect with this is that you can mix and match. You don't have to have all of the same product from one manufacturer, and as long as you've got the CAN template, then you can communicate that across. So just to show you some of this really briefly, first of all, let's just dive over to my laptop screen for a moment. This is Motec's C125 Dash Manager software, and again, it absolutely doesn't matter what product you're using. I'm just using this because it's nice and simple to show you. So what we've got is our communications set up here, and we've got on the C125, it actually has two CAN buses, CAN 1 and CAN 2. So CAN 1 here, we've got all of the different communication templates loaded up. This is all the information that we're bringing in. A couple of the ones that are important, because this ECU is communicating with 3 Motec products, which I've just circled. 2 Motec products, 2 of them are going to the same thing. So I've got M1 General on 2 different addresses that give different information. This is information being transmitted out from the M150 ECU. So basically, just about any information we could hope to want to get out of that ECU. So those 2 addresses give slightly different information. Then the third of those there is our Motec LTC, or lambda to CAN unit, giving us air fuel ratio or lambda data. So if we just click on our M1 General template for a moment, we can see over here, this is all of the received channels, and that's only a portion of them. As I scroll down, you can sort of see that all fills out. So a huge amount of information here, and this is all being transmitted across so that it can be either displayed on the dash, logged in the dash, or also used for warnings. We come down to our other template here. This is some less important information, but we've got information here around some of the rotary switches that are going into the ECU, so we can again display these positions and log them as well. Come down to our lambda to CAN, pretty straightforward here. We've got all of our air fuel ratio data, as well as information around diagnostics for that product. So that's the Motec product. But if we come down, we've also got a Haltech TCA8. So Haltech thermocouple amplifier, which is giving us our 4 exhaust gas temperatures. This is for our SR86. We're also communicating here with an ECU Master switch panel. So this is a CAN-based switch panel that goes on the back of the steering wheel. And we've got our ECU Master PMU. So this is 2-way communication as well. We've got the ability here for the dash to receive and send information out depending on what exactly we want to do. Here from our ECU Master Power Management Unit, we are logging, or we're bringing in information on the current for different channels. So if we double click on this, let's just see how that's all set up. So you can see here from our ECU Master PMU, we're receiving a message from that PMU. We have a base address for that information to be sent over. So that's pretty important. We'll have a quick look at what that data actually looks like in a second as well. But this basically defines where the dash is looking for this data in a sea of other information. Then if we go through to our receive channels, we've got those channels here. If we click on change, we can see how that data is set up. So we've got the channel name as well as the resolution for that particular channel. And then quite often we will have some scaling information here as well, so that essentially the information that we're seeing on the dash is the same as what is being sent out of the PMU. So really powerful, but I know this is also a little bit confusing for a lot of people. What we'll do is we'll just get this data up on our Dyno as well. So we head across to our Dyno, and just because I've got the version 11 STI sitting on the Dyno at the moment, we can just show this some of the data that comes through on the Dyno itself. So here we've got our ECU Master USA profile here, or template loaded up, and this is going to a CAN bus sniffer that is attached to the Dyno. And if we click on CAN bus analyzer here, this will actually give us a bit of a display of what information is coming through. Now, might all look like gobbledygook at the moment, but that's what our CAN course is going to be about. On the left hand side here, we've got our different addresses in both hexadecimal as well as a decimal output, and then you can see the data that's coming through. So again, doesn't look too useful. These are just hexadecimal values for each of the bytes of information. The ones that are being highlighted in red, these are bytes that are changing, so information that is actually changing. And this is part of the course, is going to teach you how to actually find the information you want in that sea of what looks like seemingly random numbers. In particular, that ability to see which of the pieces of data is changing at any time is quite valuable. What I'll do here is, if I just go through to full throttle very quickly, we can see as I do that, you can see a number of the bytes of information there turn red. I'll just do it again. We can see all of the pieces of data that turn red. So the process there of reverse engineering, or getting the information out of that raw CAN data stream, is what we're going to do is basically make a change to the parameter we're looking for, in this case the throttle. And what we want to do is highlight the different bytes of information that changed, and then we can get down to individual bytes and find out what the numbers are doing as we change the throttle. We'll find that some of that may be due to the drive-by-wire aspects of this particular vehicle, and we can find the particular byte of information or bytes of information we're interested in and work out the scaling. So that particular course probably still a month or more away, unfortunately, from being released, but we are working pretty hard on it. Zach will be into filming later this week. So that course works two ways as well. First of all, it's going to help you with device-to-device communication, so setting up transmit templates and receive templates between different products, which is kind of what I showed you in the Motec C125 dash software. But it will also help you with reverse engineering factory CAN bus. So again, this is getting more and more important as we move into more and more complex vehicles. So there'll be step-by-step processes for both of those options, as well as some worked examples going into that. So pretty excited about getting that course out there. We know, again, that's one that a lot of people have been asking for. Lastly, in terms of course content, Tim, just before the end of the year, was working pretty hard filming the A-roll for, or the studio work for, our advanced data analysis course. So that sort of follows on the heels of the data analysis fundamentals course, and it draws on some of his experience working in the upper echelons of professional motorsport, including the Australian Supercars Championship, World Endurance Championship, etc. So for those who want to nerd out a little bit with data, that course is going to be perfect. Again, still a little way off, but all three of those courses should be out before the end of this quarter. All right, enough talk about our courses. The other thing I wanted to mention here, or just show you, if we scoot across to my laptop screen, this is a video that we released just recently, which talks about conrod strength and talks specifically about how much horsepower a connecting rod can handle. This is a question that we get asked quite frequently. It's a question I see being posted on engine building forums regularly, and unfortunately a lot of the conrod manufacturers have actually fallen also into the trap of rating their conrods with a horsepower value, which is a problem, because when you are asking how much horsepower can my conrod support, that's not really the right question you want to be asking, because conrods really don't have a horsepower rating. What we need to understand is the forces being applied to the connecting rod, and there really are two forces being applied. First of all, under power, so when there's a lot of cylinder pressure being produced, there is a compressor force trying to basically squash the two ends of the conrod together. Obviously, the connecting rod needs to be strong enough to handle that compressive load, otherwise it's going to bend the connecting rod. And we see this a lot with factory rods as well when we start adding more power. The other load that is, I think, more often overlooked though is the tensile forces. So that's the force trying to pull the connecting rod apart. And this is what happens when the connecting rod, or the piston I should say, goes past top dead center on the exhaust stroke. So when that happens, there's no compressive load above the piston. The exhaust valves are open, and so the connecting rod is responsible for slowing that piston down as it comes up towards top dead center, changing its direction and then accelerating it away from top dead center again. So it's these loads that we really need to be mindful of. But the problem is that horsepower is not really a useful metric when it comes to defining those loads, particularly when we look at horsepower is calculated based on our torque multiplied by our engine RPM and then divided by a constant. So basically, depending on whereabouts we are making torque in the rev range, that's going to affect our power. So if you want to get a little bit more involved and learn a little bit more about what is involved in designing or speccing a conrod for a particular application, then head over to our YouTube channel and take a look at that particular video. If you've got any questions, please ask those on the video, and if you're not already subscribed to our channel, make sure you do so. Also turn on the notifications this way you won't miss out on any future videos. Lastly as well, a Instagram that I put up a couple of days ago, and this is something that we see in a lot of high-end drag cars, which is the use of these individual cylinder exhaust gas temperature sensors. So we can see we've got one there in the primary runner of each of the exhaust runners. The idea behind this, and this is something that I used significantly back when I was heavily involved in import drag racing, is that we're using the exhaust gas temperature sensors to help us with individual cylinder fuel trimming in particular. Now, this isn't really a big consideration or even a big problem on moderately powered road cars. We generally aren't running these engines at the limit. The specific power levels aren't that great, but even at that level, even with a lightly modified street engine, you're going to find that the air distribution to each cylinder is not going to be perfectly equal. And what I mean by this is if we are injecting the same mass of fuel into each cylinder, but the amount of air entering each cylinder is slightly different, of course we can expect that our air fuel ratio will be different on each cylinder. So that's a typical situation. We'll see this on all sorts of engines. It's completely normal, and again at lightly to moderately modified power levels, this isn't enough to be a consideration. However, when we get to the upper echelons of power and engine performance, and we're really pushing these engines, this can be enough to actually cause a problem. And if we've got one cylinder that is a little bit lean, it can be enough to push it over the edge. The reason that a wideband air fuel ratio sensor doesn't really give us the full story is because if we've got that mounted in the collector, it's giving us the average of the air fuel ratio across all of the cylinders, in this case all 6 cylinders. So we still do our main fuel mapping off that wideband air fuel ratio sensor, but we can use our EGT sensors to trim individual cylinders. The idea here is as we lean the air fuel ratio out towards stoic, the EGT will rise. It is effective and it does a pretty good job, but there are also a range of other factors, not just the air fuel ratio, that will also affect our EGT. So we need to take the data that we are learning from our EGT sensors with a bit of a grain of salt. Generally, I'm not chasing the EGTs too much. If I'm within about 10 or maybe 15 degrees C across all of my cylinders, I'm going to be pretty happy with that. Of course, the ultimate solution these days, since the prices have come down much lower, is to use individual cylinders under lambda sensors. There's a lot more infrastructure and stuff that goes along with adding lambda sensors to the exhaust manifold as well. Plus, of course, pre-turbocharger, their life expectancy can be a little bit more limited. So a few things to consider there. All right, that brings us to the end of our pre-show. Just a reminder there, the one last time, or for those who have joined us, the AEM CD7 dash and tuning package bundle, 14 days to run. Remember, you can get yourself into the draw by following the link in the comments. Absolutely free to get yourself involved in that draw, and we'll ship that anywhere in the world. All right, thanks for joining us. Give me a few moments and we'll get started with today's webinar.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.